The objective of this video is to introduce new ways to minimize functions at the gate level. We know that our digital logic functions are based on Boolean algebra, so we'll be minimizing Boolean algebraic expressions, and we'll find new ways to do that. Right now we know we can represent a function in terms of a truth table, which is a unique representation of any function. We can also represent a function as an algebraic expression or as a gate level schematic. And what we want to do of course, in digital logic is produce these gate level schematics. What we've done so far is we've looked at these algebraic expressions, and we can take the truth table, and directly from the truth table, get the canonical form in terms of a sum of min terms or product of max terms form of our algebraic expression. We can then use our Boolean algebra postulates and theorems to reduce that algebra to sum of product terms or product of sum terms, or other means to minimize in terms of perhaps the minimum number of literals. It's a difficult process, sometimes awkward, and does lack procedure. So what we're seeking is, can we find a specific procedure for the minimization? If we recall, if we have a truth table, here we have a function of 3 inputs. We've named the inputs w, x, and y, and our function f. We can label that as a sum of min terms by pulling out each spot in the truth table where our function is a true value or has a value of 1. And we label each of those min terms. That's at min term 1, min term 2, min term 4, and min term 7. Min term 1 is represented by, since it's wxy, w prime x prime y, or 0, 0, 1, and min term 2, w prime x, y prime, etc., as we look at each of the different min terms. Well, we can then use our algebraic postulate of distribution, and we can pull out, for example, we can pull out w prime from these two terms, and we get w prime x prime y, or xy prime, and we can pull out w from these two terms, and we get w x prime y prime, or xy. So we've used the distribution theorem. At this point, what we're looking at, we know the definition of the exclusive OR function is x prime y or xy prime, so we recognize our exclusive OR function, and then we recognize this being our exclusive NOR function. And now we see again that we have another expression where we let x exclusive OR y be some variable a, and we can use that again, and we can get from this function through algebra and our recognition of the exclusive OR function, we can realize that this function is w exclusive OR x exclusive OR y. We could also instead look at the product of max terms. Product of max terms, we find each of the max terms where the function is equal to a 0. So we say, okay, this is a product of max term 0, max term 3, max term 5, and max term 6. And then we can expand each of those max terms. Max term 0 is w or x or y, etc. And we can again use our distribution theorem of OR over and we can pull out the w or in each of these terms. We have w or x or y and x prime or y prime, and similarly here with w prime, and do the same, and then recognize again that this is our exclusive OR function. We can expand that by our involution theorem. W prime is 0, as is x exclusive OR y ANDed with x exclusive OR y prime. That's going to also be a 0. And we end up with, we recognize that this is again the exclusive OR function. So we can get this same function through algebraic means. What Karnoff came up with, Maurice Karnoff, who worked at Bell Labs in the 1950s, developing digital logic-based switching networks, came up with what we'll call a Karnoff map, or we'll refer to it perhaps in shorthand as just a kmap, a simpler method to simplify functions in terms of sum of products or product of sums. In this video, we'll introduce Karnaugh maps for 2 variable functions, and then we'll go further for 3 variable and 4 variable functions. The AND function can be represented in terms of its AND gate. We can use ampersand to represent AND, or sometimes we just put the two together, A, B, A ampersand B, or A dot B. These are the two forms we typically use in class. We can represent that as its gate. We know that this truth table is what represents that AND gate or AND function. And now we're also introducing a Karnaugh map. So a Karnaugh map has 4 cells. A 2 variable Karnaugh map has 4 cells, 1 cell for every line in the truth table. For our when A and B, which are our input variables, are both 0. AB here, we have 0, 0. This cell represents our output Y when A and B are 0. Well, output Y is 0 when A and B are both 0. So one of the things we do with the Karnaugh map is to minimize what we have to do. We don't load the zeros when we're simplifying in terms of a sum of products. So our only line in the truth table that has a 1 is when X and Y, or excuse me, A and B are both 1. So our Y is equal to 1 there. So these are our minterm 0, minterm 1, minterm 3, and then minterm 2. So these, notice here, these adjacent coding, this is gray coding, where we're counting 0, 1, 3, 2, gray coding for 2 variables. That's key for our Karnaugh maps, key for 2 variable, it'll be more key for 3 and 4 variable Karnaugh maps. When we look at our Karnaugh maps, each square represents a minterm, or we'll also see it can represent a max term. So we're working with diagrams or patterns to be able to use this map function. When we're done with our Karnaugh map minimization, we'll have the minimum number of terms, that means the minimum number of gates, and the fewest possible literals per term, or inputs to the gates. So again, our 4 squares or cells in our Karnaugh map to be able to represent 2 variables. Those cells we can consider the minterms within the cell or the max term within the cell. So here we have our Karnaugh map represented as a square instead of a straight line. If it's a function of our x and y, we have x here in vertically, x is 0 in the top row, x is 1 in the bottom row. So for our minterms, we have x prime in the top row, we just have x in the bottom row. For our max terms, however, we still have our x being 0 in the top row, but for our max term, when x is 0, we use x, since we're using x or y, and for our max terms, x or y, whatever x and y have to be for this OR product to give us a 0 in this cell. So these are how we can represent our 2 variable Karnaugh maps in terms of minterms or max terms, 0, 1, 2, 3, according to labeling of 0, 1 and 0, 0, 1 for the rows, 0, 1 for the columns representing y. So it's 2 variables. We have 2 then to the power of 2. 2 minterms, or 4 squares. We look at those 4 squares in terms of the minterms. If we have to be able to load a truth table into our Karnaugh map. So if our truth table 0, 0 is represented in this minterm 0, we have an alpha there. 0, 1, we have a beta. 1, 0, where x is 1 and y is 0, we have our gamma, and our delta, where x is 1 and y is equal to 1. So we need to be able to load our Karnaugh map from our truth table. And once we load our Karnaugh map from our truth table, we need to be able to do the minimization. So if we look at our AND function and our OR function, and here our truth tables are not labeling the zeros, they're just leaving those blank as well. And we see for our AND function Karnaugh map, we only have 1 cell loaded with a 1, and that's when at minterm 3. And for our OR Karnaugh map, we only have 1 cell that's not loaded at all, that means it's a 0, and that's at minterm 0. So we want to be able to simplify this in terms of sum of products. And so in order to simplify this, what we want to look at is what are the adjacent cells. So let's look at two ways. First, we'll simplify it in terms of the algebra, and then we'll simplify it in a Karnoff map method. For our AND function, f is equal to minterm 3, which is xy, and there's no simplification of that. That's as simple as that will get. For our OR function, we have three minterms, so we look at this in terms of f is equal to minterm 1, or minterm 2, or minterm 3. We can expand each minterm, and we can see here when x is equal to a 1, y is equal to a 0, or is equal to a 1. Algebraically, we can pull this x out using the distribution theorem, and then we know that y or y prime is, that's always equal to a 1, so we get x prime y or x. Then we can use our distribution theorem again, and we get x or x prime, and we get x or y. And we know that x or x prime is also equal to a 1, so now we've simplified this to just y or x, or we might want to write that as x or y, so it's in alphabetical order. But it's quite a few steps to go from a sum of minterms to what we call here a sum of products. Where we look at each of our product terms, and this simplified product term has one variable, and in our AND function, our product term has two variables. If we're going to use the Karnoff map simplification method, what we do is we circle adjacent ones. And again, in our AND case, there's only one 1. Our OR case is more interesting. So if we circle the adjacent ones, and our x is equal to 1 column, we see that algebraically we have xy prime or xy for the two minterms. We pull out the x, we x and y or y prime. Well, that's just equal to x. So when we do this circling, if y changes from 0 to 1, we're not going to include that. So any variable that is changing within the circle, this is just going to give us an x, and we can see why that's true algebraically. When we circle these two adjacent ones, and again that's what we circle, is just adjacent ones, we see there we're going to end up with just y is equal to 1, but x changes from 0 to 1. So that just gives us x or y, and our function is the sum of the circled products. So our function is then just going to be equal to x or y. So we circle adjacent ones. If a variable changes, the variable that changes when we encircle those adjacent ones, we don't include it in our product term. So this gives us just a product of x. This gives us just a product of y. If we look at this function, and we want to determine what this is, again, what we want to encircle is adjacent ones. So if we encircle these two adjacent ones, we see that x has changed from 0 to 1, and y is 0 the whole time. So that's going to give us a y prime. And when we encircle these two adjacent ones, x is 0 the whole time, but y has changed from 0 or 1. So we're doing a sum of products. So we do OR, and that'll give us an x prime. So we ended up with a y prime. We ended up with an x prime, and then it's the sum of the two, so that gives us the OR. So that's how we can, much simpler method. Once we put it in this map, what we're finding is what's adjacent. If they are adjacent to each other, that means that one of the variables must have changed to 0 or 1, so we've shown algebraically why that would be eliminated. So what about if we wanted to simplify into product of sums? Now we have to look at the max terms. Our max terms, 0 is x or y. Our max term 3 is x prime or y prime. And what we're looking at is what makes that function a 0. So what we want to encircle here are the zeros. So when we're simplifying in terms of product of sums, we'll load our Karnoff map with the zeros. We'll load the Karnoff maps with the zeros, and we'll want to find the adjacent zeros in the Karnoff map. So our xy, our AND function, has the 3 zeros, and our OR function only has the 1 0 loaded into the Karnoff map. And again, when we circle adjacent zeros for our AND function, here we have our y is changing from 0 to 1. and our x is staying at 0. So this gives us these two max terms, this being x or y, this being x or y prime. We show we can use our algebra. That becomes x or y and y prime, and that's just going to give us the x. So even though it's x is equal to a 0 here, since we're simplifying in terms of product of sums, this is going to give us an x in terms of a sum term. And similarly, for our, we circle these two encircled zeros here adjacent, our x changes from 0 to 1. It should not end up being included in the term. This will be included in the term, but it will be a y. Because y is equal to 0 there. So when we can show that our max term x or y ended with x prime or y prime, this is our max term 0, and our max term 2 here, max term 2, we pull out the y and we end up with just a y. So our function then is the product of our encircled terms. Key here, that's the product. So our f is equal to x, y. And again, this one's not so interesting. When we encircle that 0, we just end up with the max term. So our f is equal to our max term 0, x, or y. So it's a little different when we're looking at the max terms. We encircle the zeros, and we have to make sure when y is equal to 0 and it's a sum term, that gives us a sum term of y, as opposed to it'll give us a product term of y prime and a sum term of y. But we're encircling the zeros, so we got to use the sum terms. So let's look at loading up this Karnoff map. If we want to load up, we have a two-variable function. It's a sum of 1 and 2, so that means it's the sum of minterm 1 ORed with minterm 2. Well, we have to state, where's our x and where's our y. So we'll label x here and y here. So x is represented as a 0 in the top row, as a 1 in the bottom row. Our y is represented as a 0 in the left column, as a 1 in the right column. And so where's our minterm 1? Our minterm 1 is 0, 1. Our minterm 2 is our 1, 0. So if we can load our Karnoff map, if we try to encircle adjacent cells, there's no adjacent cells. We can't go this way. If we go this way, both x changes and y changes. So in terms, we end up with just our most minimum function is f is going to be equal to, in fact, those two minterms. So our minterm 1 being in an x prime y, or our minterm 2 being an x, y prime. If we were going to simplify this function in our Karnoff map, again, we have to label where is x and where is y. X is 0 in the top row, 1 in the bottom row. Y is 0 in the left column, 1 in the right column. X prime y, that's wherever x is a 0 and y is equal to 1. Well, that is in fact a minterm, right? So that is our minterm 1. So we go ahead and we'll load minterm 1 right here with a 1, or y prime. So y prime, that's where is y equal to a 0 as a product, or where y is equal to a 0, our function is going to be equal to a 1 there. So y is equal to a 0 both here and here. So here we can end up simplifying. When we can encircle our top row, and we end up with x prime. We encircle our left column, and we end up with a y prime, and we did this function before. So there's our simplified function, x prime or y prime. So notice if we can circle one square, then the result is going to give us a two-variable product term when we have a function of two variables. If we can encircle two squares, the result is going to give us a one-variable product term. we looked at these same functions in terms of max terms. So if we can encircle one square, then our result here is a two-variable sum term. So this is a two-variable sum term, but it's a two one-variable product terms, or the or of two one-variable product terms. So this one circle gives us a two-variable sum term. Each of these, now what we have is the product of two one-variable sum terms. Important concept. We'll look at higher order three-variable and four-variable Karnoff maps in the next videos.